What is up, everyone? Today we are going to discuss the Collatz Conjecture, also known as the 3n plus 1 conjecture, or as some may also call the 3x plus 1 conjecture. Really doesn't matter, because variables in any math conjecture, you can replace x with any variable, like t. Some people are aware of t. This conjecture was created by Lothar Collatz in 1937, according to Veritasium on YouTube. It is a very interesting one. It looks rather simple if you're familiar with something like PEMDAS, for example. Unfortunately, this is not a PEMDAS problem. It is rather a function. Like, if you're familiar with algebra or calculus, the f function, f of x, for instance. The rules are rather simple. Setting f of n with n equal to any number, or rather, f of x, as some people may call, because that's something I'm going to be familiar with because I've done math quite a lot of my life. If it were even, you divide that number by 2. If it's a positive, you multiply by 3 and add by 1. And so that's kind of where the PEMDAS thing comes from. You don't, however, set it equal to 0 if that's what you're going to assume. What this conjecture explains is it wants us to determine if two simple arithmetic operations, assuming they are repeated, I'm going to keep that in mind, turn all the positive integers, because that's a positive sign, not a t, to 1. What's unique about this is that almost any math equation that you set it up for, they always end the same way. Either 4, 2, and 1. And if it were 1, it will go back to 4. Then 2, 1. 4, 2, 1. 4, 2, 1. The cycle seems to continue. To set this up, and to try to explain this to you better, I set n equal to 5. If I were to multiply 5 by 3, that will be 15. Nothing too difficult there. Adding 1 to that equals 16. You divide that by 2, you get 8. Divide that by 2, you get 4. Divide that by 2, you get 2. Divide 2 by 2, it's 1. And this is where the loop begins. 3 times 1 is 3. Plus 1, 4. 4 divided by 2, it's 2. Divided by 2 is 1. And that's an infinite loop. I'm going to be trying this out again, but with n equal to 7. So fx equals 7, basically. 3 times 7 plus 1, because 7 is an odd number. To make things faster, I'm going to be using a TI-83 to solve this problem. 3 times 7, 21, plus 1 equals 22. And as some of you may have already guessed, 22 is an even number. I'm going to divide that by 2. Divide by 2 equals 11. That's an odd number. 3 times 11 plus 1 equals 34. And so you may be wondering, how exactly am I able to know which is an even or an odd number? It's usually the number in the units place. And I'm going to move this aside so you know what I'm doing. Now, 3, 7, plus 1, 22, divide by 2, 11, times 3, plus 1, 34. And I'm writing this crooked, so please excuse me if my handwriting looks terrible. Divided by 2, 17. Three, 17 plus 1. There, I'm going to like separate that a little bit. Times 3, 51 plus 1, 52. Divide that by 2. Equals 26. And I'm going to divide that by 2 again because that's also an even number. 13. This is actually going to be a pretty long equation, as it may look like. So if it gets down to being that long, I'm going to like skip forward. Oh, my bad. I'm going to skip forward and edit the video. Edit the video to make things faster for you, and then I'll take a few photos. Because I got a good camera after all, I'm not gonna lie about that. 3 times 13 plus 1 equals 40. That's an even number. Almost lost it there. Because, you know, some mathematicians make this problem too. They make that mistake. Here's a tricky one. Oh, would you look at that? 5. And essentially, I'm going to run it. I'm actually really close to running into that problem too. 3, 5 plus 1. And I'm almost essentially copying what's going to be here. Would you look at that? Oh yeah, give me a second. I'm going to... Three, 1. Oh yeah, I apologize if my handwriting is pretty bad. I'm usually not used to doing squiggly lines. I'm just trying to save paper. But if you ever need me to do this again, but with more spread out or easier to understand concept, you can always request and I'll redo this for you. And that equals 4 divided by 2. Equals 2, and divided by 2 equals 1. Notice the pattern here? Let's see if I can find more. And as you can see, the conjecture has been proven again. Every time the final answer of any section is 4, 2, or 1, you're going to get a loop. Now, I've actually been researching a little bit, and I would like to thank Quantum Magazine, first of all, for giving this function or writing it out this way, because that makes it easy to remember. They've also stated this, however. Although this has not been proven yet, it has been verified that n less than 268, 2 to the power of 68, would always apply with this rule. And when I've entered 268th power on my calculator, I got this gigantic number. And I've already written this out here. That number, 2.9515, I can write it like that. 2.9515 E20, or in scientific notation, 2.9515 times 10 to the 20th power. That's another name for it. Because in spite of being verified, it's still not proven. Because those two are two different things. Two different things I'll probably get onto in another video when I get the chance. So, according to quantummagazine.org, because I had to look this up because even some algebraists haven't figured that out yet. A counterexample could possibly be somewhere in 300 quintillion, because this number here, up here is already in the quintillion, so 300 quintillion is a whole other monster. Now imagine a number that big. Not as big as Google, I don't believe, but it's still a pretty big number. And therefore, if I were to attempt to do this, the video would be way too long for you guys, and I know you don't want a video that long. You could, however, take several videos, so I could try saying 350 quintillion or 301 quintillion just to be technically in this rule. But that's a whole other video. But, however, I still have explained the Collatz conjecture, the 3n plus 1 conjecture. I'd like to thank Lothar Collatz for coming up with such an interesting topic. Thank you for watching today's video. Please remember to like and subscribe, and hit that notification button for more updates.